Today we're going to introduce a new number in math called e. E is an irrational number similar to pi. It stands for about 2.7182813, so on and so forth. Okay, so e is actually a number. It's not a variable. We're going to use them with exponential functions and log functions. And when the base b of an exponential function is replaced with e, you have this guy, y equals e to the x power. Now remember our generic formula for exponential functions was a b to the x. Again, we're replacing our b with the number e right now, and a in this case is just a 1. So if we remember, our a value is our y-intercept. So that's going to be this guy right here, right? A value is our y-intercept right here. And in this case, if we plug in 1 to our x value right here, and we know e is 2.7, then that means that at 1, we're going to have 2.7, and here shows an exponential graph of y equals e to the x. Okay, if this graph represents a growth going this direction, and again that's y equals e to the x power, then a decay is going to be the opposite, or y equals 1 over e to the x power, and that's just going to look like it's going down like that. Okay, our next page here talks about common logs versus natural logs. So we're very familiar with common logs. You all know that the common log, if you just see the word log, it means log base 10. Well, natural log has its own little symbol. Natural log being log of base e of x is also known as ln of x. So ln of x is the exact same thing as log base e of x. Let me highlight this. Log base e of x is the exact same thing as ln. Okay, so let's use our calculators and let's calculate. This is now our common log, log base 10 of x. We'll use our calculator and hit log 8. And what do you get here is 0.903. When you use your calculator to find the natural log, that's going to be second ln. So, I'm sorry, not second ln. There's a button right underneath log. That's the ln button. So you're going to hit that. Hit ln 0.3, negative 1.204. And then let's try it again. You hit the ln button, so it's right beneath the log button. ln 0.75 equals negative 0.288. Now these guys here, we're just gonna treat e as we do any other number or variable when we're simplifying. In this case, the first one, we're gonna distribute this 3 exponent to both the 2 and to the e to the third. That becomes 2 to the third e to the 9th, which then becomes 8 e to the 9th. This guy, if you remember our rules, anything on top subtracts the exponent on the bottom, so this becomes e to the third power. This one here, I'm going to deal with 10 over 2. 10 over 2 is 5, right? And then e to the second over e to the fourth. What's left over on the bottom is e squared. This next one, we bring the 2 into the 5. That's going to be 5 squared. And we bring this guy into there. That's going to be e to the negative 6x power. So we can finish that one off as 25 e to the negative 6x power. This one ends up being, remember, when you multiply things with the same base, you add their exponents. So this becomes e to the 7th. And then the last one is 12 divided by 3 is 4. And e to the 4th divided by e to the 3rd is just 1 e left over. Okay. If we're going to evaluate, this is now when we use our second ln button, because like e is now being raised to the power of x plus 2. So for our first function, f of x, we're going to plug in 1. So for our x, we're going to have 2e to the third power. We're going to plug that into our calculator. We're going to hit second. We'll do the second ln. That's what we do in our calculators here. And if we plug in second ln to the third power times 2, we get 40.171. We plug in for f of 0, so 2 of the e, 0 plus 2, so 2e squared. We're going to do second ln on our calculator, squared times 2, which equals 14.778. And then the last guy, when we plug in -3, we're going to get 2 times e to the negative first power. We're going to use second ln on our calculator, and that's going to turn out to be 0.736. Okay, I'm going to do g of x in blue over here. We're going to do some more practice using second ln button. So with g of x, when we plug in g of 1, we're going to get 6e to the second power. So second ln, right? E to the second power times 6 is 44.334. When we plug in 0 for x, we're going to get 6e to the third power. On our calculator, again, second ln to the third power is 120.513. And then when we plug in -2 for x, we're going to get 6e to the, now be careful here, it's 6 minus -2, instead of being +2, which is 6e to the fifth power, which is 890.479. Okay. Graphing that natural and exponential functions, graphing natural exponential functions is going to be, similar to exponential functions as we talked about. The shape's going to look like that. If it's a growth function, these are all growth functions because they have an a as a positive number. Okay. So what we're going to do here, let me label this. Here's my x-axis. I'll just put my y-axis here. I'm going to do f of x is going to be my red graph, so we'll start there. First of all, it's nice because whatever's just plunked onto the end here, that's our asymptote. So remember, asymptotes is that wall where our graphs cannot pass. So our asymptote here is going to be y equals 2. Okay, make that asymptote like that. Oops, I don't want to do that. And then we're just going to start plugging in numbers for x. Let me get my asymptote. Y equals 2. So if we plug in, let's say 0 for x, it's going to be 3 times e to the 0 power. What's anything to the 0 power? Is 1. So 3e to the 0 power is going to be 3 plus 2, so that gives us 5. Hey, that's our y-intercept. So 0, 5, 1, 2, 3, 4, 5, that's right here. Right? 1, 2, 3, 4, 5. And then if we plug in 1, so 3 times e to the first power, e to the first power is 2.7, times 3 plus 2 is about 10.1. Right? So 1, 10.1, 6, 7, 8, 9, 10, that's about right about here. Okay. And then if we plug in, we always like to do negative numbers. I'm going to plug in -1. So 3e to the negative first power. Again, second ln is e to the x power. Put in -1 times 3 plus 2 is 3.1. So that's going to be -1, 3.1, right about there. All right. So we know it follows the asymptote. There we go. There's our f of x function. What's our domain for our f of x function? Well, all exponential functions have a domain of all real numbers. And our range has to do with our asymptote, which is y is greater than 2. Okay. I'm going to now do my g of x function. I'm going to do g of x in green. So g of x, what's our asymptote? Is this guy right here. Y equals 1. So label that. Y equals 1. I'm gonna make an XY table. We're gonna plug in the same number, 0, 1, -1, but now we're using our g of x function. So 3e to the 0 power is just 3 plus 1 is 4. 3e to the first power, e again to the first power, second ln to the first power is just 2.7-ish. So 3 times that plus 1 equals 9.15. It's like, and then we plug in a -1, 3e to the negative first power plus 1, looks like it equals 2.10. Let's graph those guys. 0, 1, 2, 3, 4, 1, 9.15, that's about here-ish. And then -1, 2.1 is about here. Okay, there is that graph. It's g of x. What's our domain of g of x? Well, it's an exponential function, so our domain is all real numbers. What is the range? Has to do with our asymptote, so our range is y is greater than 1. The last graph, we're going to do h of x in blue here. I'm going to do it above. H of x's asymptote is +2, right? So here's our asymptote. It happens to be the same as the red. That's fine. We're going to do xy chart. I'm going to plug in again 0, 1, -1 to my h of x function. So when I plug in 0, I get e to the 0 power, which is 1, plus 2, that gives us 3. When I plug in 1, e to the first power, which is again 2.7-ish, plus 2, that means it's 4.7. If I plug in -1, second ln, plug in -1 to that, and that ends up getting us 2.37. Let me graph those. 0, 3, doop, right there. 1, 4.7 is about here-ish. And then -1, 2.37 is right about here. Okay. And we go to our asymptote. Right, the asymptote. There you go. There is our h of x function. Domain of our h of x function, again, it's a exponential function, so we got all real numbers. And our range is associated with our asymptote, which is y is greater than 2. Okay. We're going to skip the change of base on this lecture because we already had that last class. And you guys had that on your homework, so we're going to skip those, which is fine. We're going to turn into the continuously compounded interest formula, which has E in it. Now, this is an important formula for banking and finances. And when you use this formula, A equals P times E to the RT, we're going to call this the PERT formula. We first have to define for ourselves what everything means. So A represents your future amount. So A is going to be the amount that you want to get after a certain amount of time with an initial deposit. So what's our initial deposit is P, okay? And then R is our interest rate, but we don't want it in percentage. We want to convert that to decimal. And then T is just how much time the money is in the account. So in our first question right here, in our first problem, how much will a $100 deposit, so $100 is our P, earning 6% interest, so the 6% is 0.06 decimal, compounded continuously. It's important to know that when you see the word continuously, that's when you can use PERT. Okay, so we know what formula we're using as soon as we see the word continuously. The next part is yielded in, how much is it going to yield in 5 years? So this is our first section. There's 2 problems here, like in one. So this is our time. So we're going to set up our equation. A equals $100 times E boop, boop, to the R, 0.06, and T, which is 5 years. Okay. So in our calculator, we want to make sure we do 0.06 first. So that would be e to the 0.3. And then now we can do second ln, 0.3 times 100. And what does that equal? That equals, we'll do this 100 e to the 0.3 power is, we'll do 1.349, and then that eventually gives us $134.99. Okay, if we do it with I'll do it in blue, with 7 years now as our time, we're done with 5 years, but we're still going to use $100. We're still going to use 0.06, but now we're changing our time to 7.5 years. Let's use PERT again because it's still continuously compounded. So 100 e 0.06 times 7.5. My calculator, I'm going to figure out what 0.06 times 7.5 is first, which is 0.45. And then we're going to end up doing e to the 0.45. Looks like it's 568. So that equals $156.83. Awesome. Let's do Joyce. We'll do Joyce here in green. Joyce's parents create a trust fund. Her P is $1,000. Okay, so we have A equals, we know it's continuously, so we can use PERT, $10,000. E, what's the rate here, is 0.09 because it's 9% interest. And how long will she have that money in there is 18 years. So times 18. So we're going to break this down. I'm going to do 0.09 times 18 first, which is 1.62. And then I'm going to do e to the 1.62 is, what does that end up being? 5.05, and so forth. So then it eventually equals $50,530.90. Lucky for Joyce. Now this last formula here is when we don't have compounded continuously. This is when they give you a certain amount of times per year. So our monthly is how many times per year things are compounded, and that's going to be your N. But everything else will be the same. Notice there's no E in here. Okay, this is not the PERT formula because it's compounded monthly. So what's our initial deposit? P. What's our interest? 0.06. It's compounded monthly, so that means N is 12. And then they're giving us two options here. We're first going to do 5 years as our time. So the formula looks a little different, but we're still going to plug in all the numbers that we know. We know our rate is 0.06. Our N we've decided is 12 because it said monthly. And then to the N, which is 12, times T, which is 5 years. That gives us 100, 1 plus 0.005 is this the 0.06 divided by 12 first to the 60th power. So equals 100, 1.005. The 60th, I'm going to do this part first. That gives us 1.34, so on. So that gives us $134.89. We're going to do it now for 7.5 years. We're changing our total time we're keeping our money in, but everything else is the same. $100 is our P, 1 plus the rate of 0.06 over our N, which is 12 months because it's monthly. If it was daily, it'd be 365. If it was weekly, it would be 52 because it's how many times per year. Okay. And then to our N, which is 12 again. And now we've changed T to 7.5 years. So what do we get? 1.005 on this guy. What's 12 times 7.5 is 90. And then 1.005 to the 90th power. What's that number? 1.566, so on. So after 7.5 years, Joyce or whoever is going to make $156.66. That's it.